All right, so welcome back, everybody. Our next talk will be on the subject From Curve Counting to Gauge Theory by Aleksander Doan from Columbia University. Alexander, whenever you're ready.
Well, thank you for having me. So the purpose of this talk is not so much to present a lot of results. I will present some, but the main purpose is to advertise the subject and to show that there are a lot of interesting questions at the interface of holomorphic curve theory and gauge theory. Everything I'm going to talk about is based on joint work from Polkuski from Humboldt University. So this is an old problem. If you give me a projective, complex projective manifold X, you're interested in how many holomorphic curves are there in that manifold, perhaps of given genus, homology class. You can put some additional constraints, for example, consider only curves that pass through certain points or other submanifolds. So this is a very classical subject going back to the Italian school of algebraic geometry and people like Grassmann and so on. And of course, the most basic example is that in CPN, if you give me 2 points, there is a unique degree 1 sphere, holomorphic sphere passing through these points, namely the line joining these 2 points. And there are other famous examples such as quintic threefolds and so on. So actually the quintic threefold is a good example because it's a case of so-called Calabi-Yau threefold. So these are 3 manifolds, complex manifolds of dimension 3, whose first Schoen class is 0. And in this case, the curve counting theory is particularly rich and particularly simple in a way because you don't have to put any constraints on the curves. No matter what homology class you choose, the moduli space of curves is always of expected dimension 0. That means that if everything, if all the equations for the curves were cut transversely, then you would expect to have the moduli space consisting of isolated points. And then you can hope for counting such curves in a given homology class and to get some sort of invariance of Calabi-Yau threefolds. And of course, this has been done. So actually, a little bit more generally, suppose now that X is a symplectic manifold, and you choose an almost complex structure on X, which is compatible with the symplectic form. So Gromov-Witten theory studies the moduli space, I call it script M, of maps from Riemann surfaces of fixed genus G, representing a given homology class A, which satisfy the nonlinear Cauchy-Riemann equation, namely that the derivative of U is J-linear. So if you first apply I, which is the complex structure on the Riemann surface, and then apply the derivative, is the same as first applying the derivative and then applying J. So we form the moduli space of such maps. And what's remarkable that there is a naturally defined compactification, I guess discovered by Gromov, but actually the idea goes back to the work of Uhlenbeck and Sachs on minimal maps. Sorry, on harmonic maps. So in any case, you enlarge the space of maps and you consider a bigger space of so-called nodal maps, which I denote here by, you can see it here, M bar. And this space is in fact compact with certain topology called Gromov topology, and it contains the actual space of pseudo-holomorphic, J-holomorphic maps. And because the space is compact, you can use it to extract from it all sorts of invariants. You define a fundamental class, and you integrate certain homology classes over the fundamental class that leads to rational invariants, so-called Gromov-Witten invariants. So here actually, I assume that the genus and the homology class is chosen in such a way that you don't have to put additional constraints on the curves. And you can show that this actually does not depend on the choice of the almost complex structure, as long as it's compatible with the symplectic form. So it's actually a symplectic invariant of the manifold. So this is something in the spirit of what I said at the beginning, that we want to count curves, except you have to count them in this very complicated and fancy way. Unfortunately, this is an invariant, but it's very far from this naive geometric intuition that I'm interested in counting some curves, perhaps passing through some constraints and so on. Because this compactification contains many more maps than just embedding of curves. And you have to count contributions from all of these, say, less geometric objects. I will return to this problem, and I will explain what are these non-geometric objects in the compactified modular space. So we do get an invariant, but there is a price to pay that it does not have an obvious geometric interpretation. In some cases, it agrees with the naive curve counting, and in some other cases, it doesn't. In algebraic geometry, there is also a different way. Namely, you can consider, instead of looking at maps and parametrizations of these holomorphic curves, you can consider them as subschemes and consider the moduli space of ideal sheaves of such subschemes. This moduli space is compact. And instead of embedding moduli space of curves in the moduli space of nodal maps, you embed it in the moduli space of sheaves, and then use similar techniques to extract invariants. And these invariants, in fact, have a very different flavor. For example, they are integer, and they don't fix the genus of the curves we're interested in, because you just look at all possible one-dimensional subschemes representing a given homology. So these are called Donaldson-Thomas invariants. And there is also a version of this invariant called the Pandari-Pandit-Thomas invariant, where you impose various constraints on the zero-dimensional components of the subscheme, because such a subschemes will have, in general, one-dimensional components, so think holomorphic curves, but also zero-dimensional components, think of just a bunch of points. So these invariants are defined using sheaf theory, and they rely on methods from algebraic geometry, and such methods are not available in symplectic geometry because there is no good notion of a coherent sheaf. So these are only defined for projective Calabi-Yau threefolds. So the motivating problems that I want to consider in this talk is the first one. Is there a symplectic invariant which counts pseudo-holomorphic curves, but is a little bit more geometric than the Gromov-Witten invariant? Namely, it doesn't have all these non-geometric contributions that I will talk about shortly. So the model for such an invariant is the Taub's invariant. Taub's considered symplectic four manifolds, and he defined an invariant of symplectic four manifolds which counts embedded pseudo-holomorphic curves. This invariant is in fact equal to the Seiberg-Witten invariant defined using gauge theory. And what is interesting is that you cannot just naively count these embedded J-holomorphic curves, because that can change when you vary J, but there is a way of putting weight on them in such a way that as you vary J, the number of curves can change and the weight can change, but the total, the sum is an invariant. So is there something like that in higher dimensions, specifically for Calabi-Yau threefolds? And the second problem is there a symplectic definition of these sheaf counting invariants that I just mentioned? As I said, they have a very different flavor from the Gromov-Witten invariants. So it would be interesting to find a definition that does not rely on sheaf theory, but rather uses ideas from symplectic geometry and analysis. So in the remaining part of the talk, I want to focus on this Calabi-Yau case, but I want to focus on the symplectic side of it. So for the rest of the talk, let X be a compact symplectic manifold whose real dimension is 6, so complex dimension 3, and the first Schoen class is 0. So the dimension is very important here because the behavior of pseudo-holomorphic curves depends strongly on that. But the condition that the first Schoen class is 0 is not very important. It happens to be the most interesting case. Essentially because of the index formula for the dimension of the moduli spaces. This is the most interesting case. So if you have such a manifold, you can choose a generic almost complex structure J, which is compatible with a symplectic form. And in fact, this is a standard result in the theory of pseudo-holomorphic curves, that for such a generic J, there will be a zero-dimensional moduli space of embedded J holomorphic curves in a given homology class. So this is a standard transversality result. And you can ask, if I have this zero-dimensional moduli space, why cannot I just count points in this moduli space? It's just a bunch of points. And why couldn't I define an invariant simply by counting these curves in a given homology class, or maybe in a given genus? And that would be much simpler than doing sheaf theory or Gaussian theory. So such a count, you always have to add signs, because two curves of opposite signs can annihilate each other. But other than that, why cannot I just count? So this potential invariant I call naive curve counting. So essentially, there are three problems with this, and I will go through each of these problems. And I will, the first two of the problems, I will say that they are not as big and you can actually deal with them. But then there is a third problem, the problem of multiple covers, which actually is an obstacle for defining such a naive invariant. So are there any questions so far? Okay.
Sorry, excuse me. So when the dimension of the moduli space is higher than 0, do we still call this counting?
Yes, that's maybe abuse of terminology, but I would call it counting. But then what you do, then you impose some constraints. So for example, you say, I look at the curves which pass through given points or pass through given submanifolds or have some tangencies. Mm-hmm. So that corresponds to integrating certain homology classes.
I see. Okay. So the constraint is the choice of homology class which to integrate to obtain the invariant.
Yes, but geometrically, it's the same as just saying, look at curves that, for example, pass through certain points.
Perfect. Thank you so much.
In this case, so the reason I chose this case, dimension x equals to 6, and the first chunk plus 0, is that all moduli spaces will be zero-dimensional in this case.
All right. Thank you.
Thank you. So what are the three problems with naive curve counting? Well, the first one is bubbling. So as I mentioned earlier, the moduli space of embedded curves can be non-compact. From the viewpoint, from a geometric viewpoint, that corresponds to a sequence of embedded curves degenerating to a singular curve. So you have to allow certain singularities. From the viewpoint of Gromov-Witten theory, if you choose some parameterizations of these embedded curves, I call them UN. So I have a sequence of curves and I parameterize them by pseudo-holomorphic maps. And I ask, can I take a limit? Can I take the limit of this sequence? And this is not always the case. Sometimes these sequences of pseudo-holomorphic maps don't converge in, say, C1, because the energy of pseudo-holomorphic maps can concentrate along a bunch of points in the surface. However, after rescaling, you can always choose a subsequence which converges in an appropriate sense defined by Gromov to a map from a nodal Riemann surface. But the point is that this nodal Riemann surface, the image of this map will in general have a different topology. So here is an example, the so-called ghost maps. So it can happen that you have a sequence of pseudo-holomorphic embeddings of tori, but they represent the same homology class. But in the limit, they degenerate to a nodal map from this nodal Riemann surface with two components. It has one component which is a torus and one component which is a sphere. And the limiting map is constant on the torus. This is called the ghost component, and non-constant on the sphere. This is called the bubble component. So what happens geometrically is that you have a sequence of embedded tori which degenerates. So the images of these maps degenerate to a sphere which is not embedded, but it has a singular point. So the singular point is where all the genus collapsed. So the homology class is preserved under this. So if you wanted to count curves in a homology class, you might be tempted to say, well, actually, that's okay because I can still count that limiting map. But the point is that this limiting map was always there. So you can always start, you could start with this. It could happen that you can have one of these spheres, and when you have this sphere, you have an entire family of maps like this because you can attach the torus component anywhere and declare them up to be constant. And then sometimes these nodal maps with unifinity can be smoothed to map from embedded tori. So this is a bad situation because in that case, for a certain j, the number of curves could change as you vary j. So this is the first problem. This is actually why these Gromov-Witten invariants are rational, and because they have a lot of contribution. Well, they're rational because of multiple covers, which I'll talk about, but also they have contributions from the moduli spaces of maps like this, the so-called ghost maps. So these are the maps that I call non-geometric because given one sphere, you can create an entire moduli space of such maps by attaching the constant map anywhere you want. So actually in this, there are some standard techniques that help you deal with this problem. So now again, I'm talking about this case when I have a 6 manifold with version class 0. And actually you can, in many cases, rule out these pathological phenomena. They happen, but they are non-generic. So as long as you're interested in generic, almost complex structures, you can rule them out. So here is an example of a result. If you have a generic J, then there cannot be a sequence of J holomorphic embeddings which degenerates to a map that I just described, a map with a ghost component and a single bubble component. And essentially the reason is, I already said what is the reason. If such a degeneration happens, then this single bubble component must have a singular point. However, for a generic J, all simple J holomorphic maps are embeddings. So this is basically the reason why this cannot happen. And you can think, well, maybe that seems like a very special case. Maybe I can have multiple bubble components. Well, if you had multiple bubble components, that would mean that you have multiple J holomorphic spheres in my manifold, which intersect. But that's also a non-generic phenomenon. So actually from this theorem that I just quoted here, you can actually show that no bubbling can happen as long as you can ignore the problem of multiple covers, which I will discuss. But if you could ignore multiple covers, actually this theorem shows that no bubbling can happen for a generic J. In fact, the theorem is a little bit stronger because it shows that it rules out bubbling for a generic family of J's. So what I'm essentially trying to say here that there are techniques of dealing with bubbling, and in this case of 6 manifolds and version class 0, because we're so constrained, because all the modular spaces are 0-dimensional and the curves generally don't intersect, that allows you to control quite well this bubbling problem. And I will not talk about the proof, but essentially the idea of the proof goes back to, in fact, it goes back to various ideas on gluing of instantons that were used in gauge theory by Taubes and Donaldson. But in the context of J holomorphic curves, these ideas appear in the work of Ionel and independently in the work of Zinger. The basic idea is that you look at, I go back. So you look at one of these U infinity, one of these nodal maps which are constant on some components, and you ask, okay, can I smooth it to an embedding of a torus? So this is a gluing problem. And there is a so-called gluing map that tells you when you can do that. And you have to analyze this gluing map. And you see that generically this gluing map has no zeros. And that corresponds to the fact that generally you cannot smooth such a ghost component to an embedding. That's the basic idea. but I will not go into this. Are there any questions about this? Okay. So this was the problem of bubbling, and I tried to argue that maybe we don't fully understand it, but one should be able to control it. So the second problem I want to talk about is the problem of finiteness. So as I said, Gromov-Witten theory deals with pseudo-holomorphic maps. To talk about pseudo-holomorphic maps, you fix some genus and you look at maps from a surface of given topology. And you can analyze bubbling and all sorts of things by considering sequences of maps from a surface of given genus. However, this entire technique that does not tell us anything about what happens to sequences of curves whose genus changes. So you could imagine that there are some pathologies, for example, that you fix a homology class and you have an infinite sequence of curves whose genus grows bigger and bigger and bigger. And in the limit, it degenerates to some very singular curve. So from the viewpoint of Gromov-Witten theory, these curves live all in different moduli space. There is no way of controlling. On the other hand, in these sheaf counting theories, the Donaldson-Thomas or Pandari-Pandya-Thomas theory, the invariance does not distinguish between curves of different genera. It says fix a homology class and look at all subschemes in a given homology class. They can be disconnected. They can have components of different genera and so on and so on. So if we're interested in the problem of finding some sort of symplectic analog of these sheaf counting invariants, then we would have to deal with curves of any genus, and we would want to say that such pathological examples cannot happen. So one solution to this is to consider pseudo-holomorphic curves as currents rather than as maps. This is very similar to the invariant that Taubes introduced in dimension 4 that I already talked about. He considered curves that are possibly disconnected and have components of different genera. And in order to endow the space, the moduli space of such curves with a topology, he used the topology of currents. So using this idea, you can prove the following theorem, that for a generic J, there are finitely many embedded J holomorphic curves in a given homology class, no matter what genus. So in fact, this pathological situation that I described, it cannot happen for a generic J. So what is the basic idea how you would prove such a result? Well, essentially, the proof is not complicated, but it uses various results from geometric measure theory and symplectic geometry that were proved by other people. So essentially, you assume that there is an infinite sequence of curves in a given homology class, possibly of any genus. Well, because a pseudo-holomorphic curve of a given homology class has fixed energy, you can take this sequence has bounded energy or bounded area, and therefore you can take its limit as currents. Any sequence of currents with bounded area has a subsequence which converges weakly. That's just what is it? That's like a Banach-Alaoglu theorem, essentially. So then, but then you get a limit which is only in a very weak sense. So it's a limit which is some sort of pseudo-holomorphic current. In principle, it could be very far from a submanifold. But there is a work of Delelis, Padares, Polar using geometric measure theory about the regularity of pseudo-holomorphic currents. And essentially what you can show is that the limit is actually an integer multiple of a smooth curve, possibly disconnected. So this is like a special case of various Allard regularity type results in about minimal currents. So once you have that curve, you can use the idea of tau. So you had a sequence of current.
Sorry, Alexander, can I ask a question? What does multiple integer multiple mean in this context?
So a current is something that associates with a two form, a number.
Okay. So it's
so
just
it will be just
integer multiple of these. Okay, fine.
yes, but yeah, it will be an integer times the integral of the form over the curve.
Right. Okay. Thanks.
Yes.
Rectifiable or something, something like this.
But actually, this is a smooth curve. It's not.
Okay, fine.
Yeah. So it's just integer times. Sorry, it will be a bunch of curves, possibly disconnected. Each of them will have an integer weight, and you will integrate the form over them.
Fine. Okay, thanks.
Yeah, thank you. Yeah, I should have maybe written more details. So anyway, once you have that curve, you start asking yourself, how did it happen that my sequence converged to that current? And the point is that you can rescale. So before you pass to the limit, you had this infinite sequence of curves. But now you have this limit curve. It has a normal bundle because it's smooth. So you can start rescaling in the normal direction. And you can find a sequence of rescalings in such a way that if you rescale your original sequence, it will converge. And in fact, it will converge to a graph of a multi-valued section of the normal bundle. So why multi-valued? In general, if you have a curve and you want to perturb it, the obvious way to perturb it, you can take a normal vector field and a graph of that. But you could also take a multi-valued normal vector field. So for example, over every point of C, you have two normal vectors. And then you could also get the graph of that, and that will be a curve in the normal bundle that is a double covering of your curve. So in general, you can, if you rescale this sequence of curves, you see that you get one of these multi-valued sections of the normal bundle. And because the curves were pseudo-holomorphic, the sections are pseudo-holomorphic. But now you can prove that existence of such sections is a non-generic phenomenon. This is related to the fact that all the moduli spaces are zero-dimensional. So in particular, if you have a holomorphic curve, you generically don't expect to have a pseudo-holomorphic normal section, because such a section would give you a deformation of the curve. Similarly, for index reasons, you don't expect to have multi-valued sections. But actually, it's very hard to show that for a generic J, all J holomorphic curves have no multi-valued normal sections. But this is called a so-called superrigidic conjecture, which was recently proved by Chris Wendell. So once you combine all of this, you see that by contradiction, you couldn't have an infinite sequence of curves, because then you would get one of these multi-valued sections which are not generic.
Sorry.
Mm-hmm.
Maybe I misunderstood, but you said something like pseudo-holomorphic normal section gives rise to deformations, right?
Yes.
So what is a pseudo-holomorphic normal section? Okay.
So the simplest case, if everything is genuinely holomorphic, so you have a complex manifold and you have a holomorphic curve, then the normal bundle is a holomorphic vector bundle, and you can talk about holomorphic sections.
Yeah, that's okay.
Here you have here the normal bundle is not holomorphic, but it still has a, it is still, because of your manifold has an almost complex structure, it equips the normal bundle of C with a Cauchy-Riemann operator. And that's the, so a section which is in the kernel of that operator I call pseudo-holomorphic.
Okay, but this doesn't square to zero, or it's so?
Yes, sorry. It does square to zero, but it's not complex linear in general.
Oh, okay. Thank you.
Thank you. Thank you for the question. This is the same as the deformation operator of the curve, essentially.
Yeah, yeah, okay.
Thank you. So that's the basic idea of the proof. Are there any other questions about this? Okay. So let me check the time. Actually, so I talked about this finiteness and so on, and I said it's here. I said it's important for these DT and PT invariants if you wanted to have some subjective definition. But actually, Gromov-Witten theory is perfectly fine without these considerations because it always considers curves of fixed genus, and then you can use Gromov compactness to study these questions. But actually, this problem of finiteness is also related to Gromov-Witten theory because of the so-called Gopakumar-Waffa conjecture. Without going into the details, this conjecture has two parts. Part A says that the Gromov-Witten invariants can be expressed in terms of some other invariants, which are integers. So this is important because Gromov-Witten invariants are rational, and these other invariants are integers, and there is a universal formula that you can just write down, which relates the Gromov-Witten invariants in terms of these integer invariants called the Gopakumar-Waffa invariants. So this is something about the structure of the Gromov-Witten invariants. And then there is a second part of the conjecture which says that these invariants should vanish for a sufficiently large genus. So they're also parameterized by genus and homology class. And if you fix a homology class, the conjecture says that these invariants vanish for very large G. So it's something like these invariants want to count embedded curves, and they want to tell you that there are only curves of, there cannot be curves of arbitrarily high G. That's essentially what this conjecture says. And the first part was proved by Aaron Parker, but the second part is still open. And actually our result shows that the second part is also true when A is the so-called primitive homology class. I don't think I have it on the slide, so let me tell you what the primitive homology class is. It means that it's not a integer multiple of another integer homology class. So what I guess my point here is that even if you didn't care about these DT invariants and so on, having some sort of control of the curves as the genus goes to infinity can be also relevant for Gromov-Witten theory. So that was a digression. So let me, So I discussed two problems with naive curve counting. I said, first of all, if embedded curves can degenerate, that's bubbling. And second, there could be infinitely many of them as the genus goes to infinity. And then I said, actually, we have some solutions to, maybe not complete, but some understanding of these problems. So actually, the two theorems I already stated would be sufficient for showing that if you fix a homology class, you can simply choose a generic J and naively count the embedded curves up with the signs, and that would be actually an invariant. This number actually would not depend on the choice of a generic J, as long as this homology class is primitive. And there is actually an earlier result of Zinger, which shows exactly that, except it relies on the fact that the Gromov-Witten invariant does not depend on J. But from just the two results I already stated, you could already prove that. However, when A is divisible by some integer, where it is a integer multiple of another integer homology class, the naive count is not an invariant. And this is related to the third problem I want to discuss, the problem of multiple covers. And this is the most interesting of the three problems. So for simplicity, I will only discuss covers of degree 2, because all the essential features you can already see there. So suppose that A is not primitive. So suppose that there is a homology class B such that A is equal to 2B. Then what can happen is that you can have a sequence of embedded pseudo-holomorphic curves representing the homology class A, which degenerates to a double branch cover of an embedded curve in the homology class B. So from the viewpoint, for example, of currents, that would mean that these embedded curves as currents converge to 2 times the curve in the homology class B. So the picture I show here is, I think, from one of the papers of Pandaripan and Thomas. That's from the viewpoint of subschemes that you can have a series of these equations describing an embedded curve, but as you vary the coefficient of the equations, you get a subscheme which is two times the solution to the equation. This is a cartoon what happens. So even if you were optimistic and you said, well, this couldn't happen for a generic J, this can still happen as J varies. And as it happens, here I would have a sequence of curves in class A, but in the limit that curve would disappear from my moduli space, so the count would change. So that means that as J varies, my naive count would not be an invariant. Of course, you could say, well, why don't you just count this curve with weight 1/2 or something like that? And that's exactly what Gromov-Witten theory does. And of course, the problem is that my covers can be also branched. So they also come in a moduli space. And of course, you can count them with rational weights, and that would recover the Gromov-Witten invariance. But that's not what we want to do. We want to have some sort of count of embedded curves. So in the last few slides, I will describe a proposal or a conjecture of how we could fix this, how we could define something which some kind of count of embedded curves with weights in such a way that that should be an invariant as J varies. So this would be similar to the four-dimensional invariant that Taubes introduced that I already talked about. So we want to correct the naive count. The naive count just takes embedded curves and counts them with signs, or maybe some other weights. But the simplest thing to do is to just equip them with signs. And we want to have a correction term which jumps exactly when I lose one of the curves because it degenerated to a multiple cover. So again, suppose for simplicity that I don't care about covers of higher degree. For example, that A is 2 times B, where B primitive. That means that there cannot be higher degree covers in my class A, only double covers. So I want to define an invariant. We would schematically look like this. So I choose a almost complex structure J. And first of all, I count the first term. You simply count curves, embedded curves in class A with some weight depending on the curve and on J. So in the simplest situation, that could be just ±1, where there is a natural way of equipping the modular space with orientation, and that's, for example, you could choose that way. And as I try to argue, this should not be an invariant because embedded curves in class A can degenerate to a double cover curve in class B. So then I want to add some weight W2, which counts embedded curves in class B in such a way that when I lose one of these terms, I gain something in one of these terms. So I think this is explained here. Suppose that I have a family, what do I want these weights to do? Suppose that I have family JT, such that as T varies, I have a curve C tilde in class A, which degenerates to 2 times C, where C is a curve in class B. So I want, as J varies, to this number be preserved. That means that if I look at the weight of the C tilde plus the weight of C with respect to the initial almost complex structure, that has to be equal to the weight of C with respect to the final almost complex structure, simply because this curve, C tilde, degenerated and it disappeared from my moduli space. If I could find my weights in such a way that this is satisfied, then this number at J0 and at J1 would be the same. Are there any questions about this? So how to find such weights? So for that, you have to understand what happens when this degeneration happens. So suppose that we are in this situation, then very much as what was already talked about, when such a degeneration happens, you can start rescaling in the normal direction of this curve C, And you will see that there is a two-valued J-holomorphic section of the normal bundle. So here I write it as a map to the symmetric product. So that means that over each point in C, I have two vectors in the normal bundle. And these vectors remember the directions where C tilde came from. In other words, this way W2, so right, I should say, the existence of such a two-valued section is clearly dependent on J because this section has to satisfy PDE, which depends on J. So as I explained with the superrigidity conjecture, you expect that for a generic J, there will be no sections like this because the index of this operator is 0, but as J varies, you might produce some sections. So the point is that we want to associate with a curve C and an almost complex structure J, a weight which changes exactly when I encounter one of these two-valued sections of the normal bundle, satisfying the J-holomorphic equation. So a very similar problem was studied in G2 geometry by Heides and Walpuski. They were interested in either counting G2 instantons or counting associative submanifolds of G2 manifolds. And unfortunately, I won't have time to go into details, but essentially they produced a general way of finding equations which jump exactly when I have a phenomenon like this. So you're looking for some kind of equation whose count of solutions will change exactly when I encounter one of these sections. Now the point is that the normal bundle has rank 2. So because I'm in a 3 manifold, in a complex manifold of dimension 3, so this is a complex rank 2 vector bundle. And the main point is that the symmetric product of C2 is actually a hyperkähler space, and it can be written as a hyperkähler quotient. And now what Heides and Walpuski did, they essentially said, anytime I have a map to a hyperkähler quotient, which satisfies certain natural PDE, I can produce a system of equations whose solutions should jump exactly when I have such a map. So actually, if you go to what they wrote and you try to unravel everything, you find a system of gauge theoretic equations on the Riemann surface, which it doesn't really matter exactly, especially what they look like, but the point is that it's some sort of a vortex type equation. So you have some section alpha, beta, psi. They have to satisfy the del bar equation. They have to satisfy some algebraic equation that's essentially the complex moment map equation. And they have to satisfy some kind of vortex type equation. So this is like a mixture of a vortex equation and Hitchin. If you look at this term, it looks like Hitchin's equations. So again, what do we want from these equations? We want to count solutions to them on a given C. The number of solutions we call W2, and we want this number to jump exactly when I have one of these multi-valued sections. So in the last slide, I will try to briefly explain why we should expect that to happen for these equations. So as I said, it doesn't matter very much what these sections are, but essentially the only way for the count of solutions to this equation to change is when one of the sections goes to infinity. So I have sections alpha, beta, and psi. And actually you can show that alpha and beta must be bounded. So really the only bad thing that can happen is when the norm, L2 norm of psi goes to infinity. This is the same as for Hitchin's equations. The only way you can go to the infinity in Hitchin's moduli space is when the section, the L2 norm of the section goes to infinity. So suppose that you have a sequence of solutions such that the L2 norm of the section goes to infinity and rescale everything. In other words, you neglect everything that does not go to infinity. So because alpha and beta are bounded, you can set them to equal to 0. So here you set alpha, beta equal to 0 and also set A equal to 0. So the connection also does not go to infinity. So essentially what you recover is this. These are the limiting equations. Now I actually should explain what is Xi. Xi is a section of the normal bundle tensor endomorphism of some rank 2 bundle. So what I was trying to explain now is that if I lose compactness for these equations, if the number of solutions changes, I should see one of solutions to this limiting equation. But now we see what it is. That essentially tells you, so N is the normal bundle has rank 2. And E also has rank 2. That means that I have two matrices. At every point I have two matrices. And these two equations tell me that these matrices are normal and that they commute with each other. That means that I get two eigenvalues. And over each point in the curve, I get two eigenvalues that give me an element in the normal bundle. So this is called the Hitchens spectral curve construction. Sorry, I think I said it wrong. So I get in total, right, each matrix has two eigenvalues, but then I tensor with N, so I have 4 of them. So that gives me 2 points in the normal bundle. I'm sorry, I misspoke. This is essentially the same as Hitchens spectral curve construction. So the point is that over each point I have over each point in the curve, I had 2 points in the normal bundle. That gives me a section of the symmetric product. So this is a very imprecise argument why, looking at these equations, if you lost compactness for these equations, you would expect to have a section of the symmetric product. So there is a conjecture, precise conjecture here to be made, that if you fix a Riemann surface C and you study the moduli space of these equations, for a generic J, you should be able to count them. But at certain J's, and these are exactly the J's for which there exists a section of the symmetric product, the number of solutions would change. And if this is the case, then I'm going back to the previous slide. If this is the case, then this weight would have exactly the behavior that we wanted to have. And that would mean that this number PT is an invariant because it does not depend on J. And moreover, we conjecture that this number, if it can be defined, is equal to the Pandari-Pandit-Thomas invariant in algebraic geometry that I already briefly mentioned.
Sorry, one question.
Mm-hmm.
When you say such data is equivalent to such a section, is it any kind of section, or is it again something like pseudo-holomorphic section?
That's a good question. So here what I wrote is just algebraic equations. So as such, that solutions to such algebraic equations would be equivalent to a section. But if you look at my equations, it also had an equation for Xi to be pseudo-holomorphic.
Okay.
Now, if I rescale it, I also get something that satisfies these algebraic equations plus the equation of being pseudo-holomorphic.
Okay.
So in the end, it will produce a pseudo. Yes, thank you.
Thank you.
That's a good question. Anyway, so this is a conjecture, and I think it's an interesting problem to study compactness for these equations. And actually, this is related to a lot of recent work done by Taubes, Heidesveld, Puskin, Zhang on the study of so-called generalized Seiberg-Witten equations, which exactly have this property that the modular space is non-compact, but we know what causes the non-compactness. So I think this is a nice problem at the intersection of holomorphic curve theory and gauge theory. And yeah, let me finish there. Thank you.
Thank you very much for the talk. Let's congratulate the speaker. Are there any questions?
I have a question about this. So this jump that you mentioned, you've explained why you might expect there to be a jump, sort of roughly why there'd be a jump when you have this section. which would compensate for this multi-valued section. But why should we expect that it jumps by the same amount? If that makes any sense, like you need to compensate exactly rather than just.
Right. That's a very good question. So actually, this is, of course, I cheated a little. So in the naive count, this W1 would be just plus minus 1, depending on the sign of curve.
Mm-hmm.
But that's actually not what we want to do. So we want to equip, this is related, in Thomas theory, so you go and look at the papers in algebraic geometry and you ask, what is the weight of just an embedded, unobstructed curve in, say, Thomas theory? And you find some expression. And actually, when you look at this expression, you realize that this is the same as the Seiberg-Witten invariant of the 3 manifold, which is the curve times S1. It just happens to be that. So now you want this equation, when it jumps, you want it to jump exactly by the Seiberg-Witten invariant of this curve C times S1. And that's exactly where these sections alpha and beta appear. Because what happens when you have this jump, the jump is, philosophically, the jump is caused by psi, but how much is jumped is caused by alpha and beta. So now in these equations, let's set psi equal to 0. Then what you get are just the vortex equation, the standard vortex equation on a Riemann surface. And the standard vortex equation is actually a dimensional reduction of the Seiberg-Witten equation. So these additional sections, alpha and beta, which I neglected, actually tell you how much it should jump.
One all related to the Seiberg-Witten equation, solutions to the Seiberg-Witten equations, or reductions of them.
Right, exactly.
Interesting. Cool. So that's really interesting.
You really need both. In my discussion, I neglected alpha and beta, but that's really fine. Yes.
Cool.
Are there any more questions?
I have a question. So what by Heidis and Walpusky was theorem and what's conjecture? Because I mean, if you figured out the G2 case, then you have the Calabi-Yau 3 case, right?
Yeah, in the G2 case, almost everything is conjecture. So they study a slightly different set of equations, and they have a compactness theorem for these equations, which essentially says that you lose compactness for these sort of equations when anytime you have this sort of section. So this is part of actually what we want. Their theorem is, and that's actually based on this work of Taubes, and there's also a paper about Walpusky-Zhang. This is just a general gauge theory question. Give me a system of generalized Seiberg-Witten equations, and when do I lose compactness for those? So there are lots of results in this direction. In dimension 3 and 4, this is actually a very hard problem because when you lose compactness, you want to say after rescaling, you converge to something. But that convergence actually takes place outside a certain singular set. In dimension 2, the singular set, there is not much space. So the singular set will be always just a bunch of points. So the problem is easier. And this will be, in fact, exactly the points where your cover is branched.
Okay.
I don't know if, sorry, maybe I...
No. It does answer the question, yes. Yeah, thanks.
Thank you very much. Are there any more questions? If that's the case, then we'll move on to the break. Thank you very much for the talk, Alexander. It was very nice.
Thank you. Thank you for having me.
Of course. So now we're going to move again to the breakout rooms. So everybody will get the notification to move to the breakout room in a few seconds, and we'll reconvene for the next talk in half an hour.